would correlate with experiment 2's data on this table, noting that experiment 1, which is what we've been doing this question up to this point, that titration curve is already given to me. So this question is not too bad because what we've noticed is that in experiment 2, we have doubled the grams of sodium hydroxide, and therefore we've doubled its concentration because it's happening in the same volume. So if we remember from the previous question, our equivalence point of experiment 1 is at 16 milliliters of base added. So because I've doubled the concentration of base, my new equivalence point will be at 8 milliliters. Okay, so when 8 milliliters of base is added, it's halved because I've doubled my concentration. And so that actually means, remember, this was my old half equivalence point. So my new half equivalence point will occur at 4 milliliters. So my graph will look, it'll look similar, but it'll look something like this, okay? At the equivalence point, at the new equivalence point, this will shoot up, and then the rest will look the same when the base is excess. The answer key online looks better, but this will hopefully give you an idea of the logic of the answer. Now, the next question is a lengthy one, but it is a classic calorimetry question. So this question, it's easy to solve, but there's a lot of things going on, and you really want to understand why we're using the values that we're picking. So what this is saying is that we're mixing a certain volume and concentration of lactic acid with an initial temperature with the same volume and concentration of the base at the same initial temperature. We measured the final temperature, and we have a specific heat capacity of water given to us, and we want to know the heat produced in the reaction in joules. So you guys, the variable for heat is Q, and in this question, it's actually Q of the surrounding, which I'll label Qsurr, equals MC delta T. You can look that up on your data sheet, on your formula list, okay? Now, why did I label it Qsurr? Because you have to distinguish between the system. The system is sometimes labeled as RxN versus the surrounding. The surroundings are usually water, okay? So water is where we can capture a heat transfer, and that is usually in a real lab setting where we actually measure temperature data. And so where it says system or reaction, this is the actual chemical reaction you're doing, but it's hard to measure that. So it's actually, I don't think it's possible to measure that at all. So we measure the surroundings to figure out our heat transfer. So the Q of the surrounding in this question is going to equal 200 grams or 200.0 grams, because what you've noticed here is you have 100 milliliters of acid, okay, which, by the way, this is aqueous, which means it's dissolved in water, mixing with 100 milliliters of base, which is also aqueous. And so when you put those together, it's the aqueous part that is the surroundings. And also, because you're mixing acid and base, you're getting water as a product. So that water is the surroundings where we are capturing, our temperature data, and that's where we're measuring the heat transfer. That's also why we use this value here for specific heat capacity. 4.2 joules per gram degree Celsius represents the specific heat capacity of water, and my temperature change is final minus initial. So 23.2 degrees Celsius minus 20.0 degrees Celsius. And yes, put the units in as you're doing the calculation so they understand where you got the final units from, because grams cancels out and so does degrees Celsius. And I'm left with a Q of surrounding of positive 2,700 joules. Okay? Now, in the next question, I'm being asked to find the enthalpy of the solution, or excuse me, the enthalpy of the reaction expressed in kilojoules per mole. Include the sign in your answer. Okay, so this is important. So first of all, enthalpy, the formula is delta H reaction equals Q of reaction over moles over N. So I have to do some work on the side because if you remember up here, the reason I labeled this Qsurr is because we calculated the heat of the surroundings. So we need to change that to heat of the reaction by understanding this relationship. That if the surrounding gained 2,700 joules, the reaction lost 2,700 joules. So Q reaction equals negative Q Qsurr, which means that Q of reaction equals negative 2,700 joules, but I'm going to change it to kilojoules because my final answer and my standard unit is kilojoules per mole. So I'm the decimals here, 1, 2, 3, negative 2.7 kilojoules. What about the moles? Well, remember that moles equals concentration times volume, and if we go up here, I'm given the volume and concentration of both the acid and the base. Now, you guys, you would have to use the moles of the limiting reactant, but they're both limiting because you have the exact same amount of both, and it's a 1-to-1 ratio. So when you calculate the moles, it doesn't really matter which compound you're doing because they're both limiting reactants. So what I'm going to do is I'm going to take this 0.500 moles per liter. And remember, it was in 100 milliliters, but we're going to change that to liters so the units cancel properly. Okay, and then I get my mole value. Now we're going to plug these into our enthalpy equation and calculate the enthalpy of reaction. And it's negative 2.7 kilojoules over 0.0500 mole. Delta H reaction equals, the answer will be negative, which, by the way, that means it's exothermic, meaning that you released energy in this lab or in this neutralization. And we get negative 54 kilojoules per mole. The negative sign means reaction is exothermic. Now you can also tell, by the way, it's exothermic because the thermometer's temperature, you're measuring the temperature of the water. Okay, remember, so you're doing this little lab, you have your thermometer here. So the water is the surrounding, and the surrounding's temperature, it went up. It went up around 3 degrees, right? So the surrounding got hotter, which means the reaction lost energy, okay, which means it's exothermic. Okay, final question here. The student, okay, this is a little wordy again, but it's basically saying that the student claims if heat is lost from the calorimeter to the surroundings air during the reaction, then the experimental value of molar enthalpy of reaction will be smaller than the magnitude of the actual value. Do you agree or disagree with the student's claim? So, first of all, I think we need to figure out what do we mean by experimental value and then actual value. This means if you are doing a lab, so if you're doing this exact lab and calculating and trying to figure out delta T and doing this, mixing these chemicals together and measuring the temperature and all of this, let's say you get, I don't know, a temperature instead of 23.2 degrees, you get 22 degrees or something. So then you'll go through this whole calculation and you'll find your delta H. So this actual value is what you get from a real lab situation. This experimental value is, another word for this is theoretical value. So theoretically, if I did this experiment perfectly and my volumes are correct and my concentrations are accurate, okay, and theoretically, and if I started at 20 degrees Celsius, then theoretically I should get this experimental value of this negative 54 kilojoules per mole. But the student is actually correct because you guys may remember that when you're doing a lab, this is true. This is true. Unless you have an airtight seal, which I think is impossible, you will lose additional heat to the surroundings beyond the water. So heat will go into the air, heat will go into the beaker, heat will just be lost to the surroundings, and our temperature data may not be as accurate. So the answer is yes or agree. And the reason is because if you lose heat out of the calorimeter, then I'm going to just point form it, okay? So you guys can look at the answer key to get the full detail. But basically, if you lose heat to the air, then TF that you measure, or TF that you gather, it will be most likely less than 23.2. Okay, because a lot of that heat has left the experiment, and so the student is correct. This is a valid source of error. All right, I hope this is helpful. Please watch for the next question if you're interested. Thanks.